I think we can start.
Okay, we can start the webinar. Welcome everybody. This is Omicron Lab, and today we have a webinar for the first time ever with a guest speaker. In fact, this is a very great webinar for us because we just have to do the introduction.
And we'll learn a lot of things.
Yeah, absolutely. So, and Ali has to do all the work.
Yeah, that's great. That's even the best part of it.
Okay. Therefore, we already hand over to our friend, colleague, and mentor Ali Shirsavar.
Hi, everybody. My name is Ali Shirsavar. I am a senior lecturer at the University of Reading, and I'm also the director of Biricha Digital Power. We provide training in forms of various workshops, analog design, power supply design workshop, digital, PFC, and so on. But recently, we've been working a lot on a new piece of software called Biricha WDS. And this particular piece of software allows you to design analog and digital power supplies very, very quickly. It's quite unique in the sense that as well as allowing you to start design a standard analog topologies, it also can do isolation, so you can have isolated power supplies, and also you can design digital power supplies. So I'm hoping that you can see my screen. Naomi, can we see the screen? Yeah, very good. Okay, so let's start with, no, we're not going to talk about the workshops. Excuse me, these are not meant to be here. Okay, introduction to WDS. WDS has been designed as an ultimate toolbox for power supply design. It designs a whole host of different topologies. Excuse me. It automatically calculates poles and zeros as well as component values. It's got sophisticated control algorithms to stabilize analog and digital power supplies, automatic coefficient calculations for both floating point and fixed point processor. At the moment, we have got a tab for TIC2000. We also have a tab for microchip, and we can do generic 32-bit and 16-bit processors. We can do automatic compensated design for isolated power supplies with TL V431, LMV431, TL431, and a host of other industry standard optocouplers. And of course, you can do simulations in time domain, you can do simulations in frequency domain, and of course, you've got the ability to superimpose your frequency domain simulations with the measurements from a Bode 100, and that is what we're going to demonstrate today. So the interface will look something like this. I will show you the details in a minute. You have got a bunch of tabs over here whereby you set up your specifications, and after that it will recommend for you various component values. It will design a controller, and it also gives you the nearest preferred values for the compensator. You get a Bode plot on the right-hand side, and you will see soon that it will give you all the information with regard to stability as you go through. This is what I've taken off from the specification tab. Around here, you can have a buck converter. You type in your input voltage and your output requirements. You type in your efficiency and overshoot that you're willing to allow. Then you select your control mode, whether it's voltage mode, current mode, analog, or digital. You give it your desired switching frequency and crossover frequency, and it will go away and it will design for you pretty much everything that you need. In particular, given the efficiency requirements, it will tell you what your RDS and the rise time and the file time should be under. And based on that, you can go and select your components. It will also tell you what your output capacitance should be. Again, based on that, you can go and select your components. So it provides you with all the stresses on the components. You can see over here that you've got all the stresses on the component. This is on the primary switch. That's for a diode. Then, when you move on to the next tab, you have got the output filter inductor, and you've got the output capacitor. Of course, for a buck converter, this is the output choke and a bunch of electrolytics. And here again, based on the ripple requirement that the user types in, it calculates the desired value of the inductor. And of course, the user gets to choose their own value that they have taken. For example, this is a part that we found in the VERT catalog, 22 microhenries, 70 milliohms of DCR, and you type that in, and based on that, WDS will then recalculate all your poles and zeros. Same applies to your capacitance. In order to meet the ripple requirements, WDS is telling you that you need around 500 microfarads of capacitance, and what we have selected is 440, that is 220 in parallel. We measured the ESR with a Bode 100. The ESR for one capacitor was 68 milliohms, and of course we have two of them in parallel, two identical ones, therefore the overall ESR is 34. So again, as soon as you type these in, the WDS will calculate all the necessary information for you. In particular, it calculates the position of the ESR 0. This is very, very important for your stability, which we'll see in a minute. It calculates it gives you the specified overshoot and the actual overshoot, and in the specification tab, you will have selected two things. You would have selected, one, the desired overshoot, and two, the desired ripple. And these two are conflicting. So if you look at the bottom, what it says is that it says calculated capacitance is based on the voltage ripple requirement to meet both overshoot and voltage ripple specification. What this means is that you have selected a power supply with a very small output ripple, and therefore the output ripple has been used as the worst case scenario in order to calculate the value of the capacitance and the ESR. And then you have got the RMS current and the ripple current, and of course this is what you need in order to select your capacitor. So far, within a few minutes, we have managed to select the semiconductors, the FETs, the diodes, the output inductor, and the output capacitor, but we still have to calculate the positions of the poles and zeros in order to design a stable power supply.
Ali, we got the first question on the chat function. So the question is, what about DC bias and cap value derating, assuming need to enter derated values?
No, at the moment we are talking about the output capacitor, which is an enormous electrolytic capacitor. The DC bias comes into play when you are dealing with large ceramics. So I have got 440 microfarads of electrolytic capacitance. So at the moment I am not worried about the DC bias.
In case you're worried, you need to enter the derated value into the software.
That's correct, yes. That's correct.
Thank you.
Okay, thank you.
Okay, so what we have got is a type 3 compensator. This is what WDS has chosen for you. And the PWM ramp height, WDS will calculate on the voltage mode based on what you type in from the data sheet of an analog compensator. So if you're designing an analog controller, you have to type in the height of the ramp from the data sheet. If you're using a digital controller, then this value is normalized to 1 volt, and then WDS will look after it in the transfer function in order to calculate the coefficients of your digital power supply. So based on that, you can see down here that you have a bunch of poles and zeros that WDS has automatically placed for you in order to get the desired crossover frequency and the phase margin, and you specify that in the specification tab. I will do a live demo in a minute shortly. And then on the next tab, you have got the reference voltage. Again, this is user-defined and is based on your chip. And the potential divider that goes into the analog IC. And that one is decided based on the user's requirements of how much current you're willing to pass through these two potential divider resistors. And of course, you decide that based on how much power loss you're willing to have. Somewhere around 60 milliwatts is something that I'll be happy with a 08 or 5 or let's say 1206 package. And based on that, it calculates the potential divider values, and it has also calculated all of the component values here, which should give you the right poles and zeros over here. But of course, these are not the nearest preferred values. These are the calculated values based on exact position of the poles and zeros. So when you go and select the nearest preferred values, then your Bode plots will change, and therefore down here, WDS will display the actual poles and zeros as opposed to the theoretical poles and zeros. And you can see there is a marginal difference between the two. For example, the polar origin from an ideal 3,979 has moved up to 4,300, and that is because you are using a different value of the nearest preferred value of the component. And then, of course, in order to test everything, we're going to measure it. We will do that live in a minute. You probably will have seen this before. You put an injection resistor, you put an injection transformer, and then you have got your network analyzer, which injects the signals, and then you've got your channel 1 and channel 2, and this is the result that we got. Now, over here, you can see the blue trace, and the blue trace is the simulation from WDS. So the blue trace is the what we have calculated, and the black trace is what we got from the Bode 100. And you will see that around the crossover frequency, in fact, we have got an almost perfect match. This is an absolutely perfect match. Around the resonant double pole, you will see that the resonant bump on the simulation is higher than the bump on the actual measurement. And you can also see this effect on the phase. The phase drop on the simulation is a lot sharper than the phase drop on the actual measurement. And of course, the reason for that is that we have typed in the DCR value of the inductor, the DC resistance of the inductor, but of course, we are now dealing with the AC resistance of the inductor, which is higher. Therefore, you have a lower Q because you have more damping. And the effect of damping is that it reduces the height of the bump, and also it shallows out the phase degradation. So this is exactly what you expect to see. This is the compensator. Again, now the red trace is what WDS has calculated, and the black trace is the real measurement from the Bode 100. And you can see that we have got an almost perfect match between what we have calculated and what we have measured. And finally, the loop. The loop is my plant plus my compensator. And here, again, I have got the black trace, which is the measurement from WDS, the measurement from the Bode 100. Green trace is from WDS. I have already explained why the double pole bump is lower. And you can see that afterwards I've got an absolutely beautiful match. WDS will display for you two vital bits of information on, on the top of the Bode plot. First, it gives you the nominal value of the crossover frequency, the phase margin, the gain margin, and the slope at crossover frequency. Right-hand plane 0 is not available on a buck converter, so you don't have to worry about it. And then it gives you the measurement, and you can see the correlation between the measurement and the simulation, and you can see that it is matching almost perfectly in all of the values that you're interested in with regard to stability. The other thing that it gives you is the worst case values, the maximum and minimum. And this will come to play when I do a live demo and I type in different values of input voltages, and you will see that it gives you the lowest crossover frequency, the highest crossover frequency, the lowest phase margin, the highest phase margin, and that therefore you can have a good estimation of what is your worst case scenario before you have even designed and built the power supply. So we are now going to do a live demo, and for that, I need to close this momentarily. Here is WDS. For now, let's quickly design a buck converter. I will do a flyback very shortly. Here are the topologies that we support at the moment. What we are going to add very soon is going to be boost, and also we're going to add PSC boost, continuous conduction board PSC as a boost topology. So let's do, for now, let's do a 12 volt power supply. Please bear with me. Let's do 5 volts. Let's do 4 amps. And you can immediately see that every time I change something, it will automatically change the body plot. For example, if I change my crossover frequency to 10 kilohertz, it will automatically change the crossover frequency to 10 kilohertz. This line here represents my crossover frequency, and you can see the crossover frequency up here. So if I change my phase margin to 55, if I put a silly number like 555 degrees, then WDS here will give you lots of warnings to tell you that what you're trying to do is unreasonable. So if I do 55, you will see that it will automatically recalculate everything and is now displaying 10 kilohertz, 55 degrees. Okay? Let's say that I change my demand efficiency to 90%, and immediately over here you will see that it will give you a power loss budget. So if I turn that back down to, let's say, 80%, it shows you how much you have lost and how much you have got. Okay, so let's make it a little bit tougher, and let's say that we want 90%, and you will immediately see that you have actually used up quite a bit of your power loss budget. On a buck converter, I do not have a transformer, so I will talk about that when we do a flyback. And on the semiconductor tab, it has given me what the values of my semiconductor should be lower in order to give me the power loss that I am demanding. And it tries to balance this. So what the software is trying to do is trying to make sure your switching losses are almost equal to your conduction losses, and also the losses in the semiconductor are almost equal to the losses, let's say, in the transformer or the losses in the snubber. So it tries to spread out the losses as much as possible. So let's say we have an on resistance of 100 milliohms. Let's make it a little bit worse. Let's say we have got an on time of 15, the rise time of 15 nanoseconds, and the fall time of 15 nanoseconds. And let's say that we have got an output capacitance of, I don't know, 150 is a reasonable number. And now you can see that you've actually, in fact, gone above your power loss budget. You're losing a little bit too much. But let's say that I use a very nice diode, and the forward drop on the diode is a lot lower. And at 0.4, again, you'll immediately see that the power loss budget is now underneath what you expected. So you, at the moment, you're meeting the specification, but you don't have much to spare room. You are saying that you have got, you are demanding 25% ripple on your inductor, and based on that, WDS has calculated an inductance of 15 microhenries. So that your user can type 15. Let's keep that as it is, and then here I have got a amount of capacitance. Let's say I use 660 microfarads. That will be 330 in parallel with one another, and that sounds like a reasonable ESR for me. I know the position of the ESR. I know all the specifications I need in order to go and buy my capacitor. In particular, I know the amount of ripple current, the peak voltage on the capacitor, and so on. Then we go to the next tab, and here I have got the PWM ramp height. That comes from my PWM chip. 1.8 is pretty much standard. The older chips used to be 3 volts. Now everything is a lot smaller. And over here, WDS has calculated for you the values of the poles and zeros. And these are the values with automatic placement. Of course, if you wish to place your own poles and zeros, then you can do so. What you do is you click on manual pole placement. It gives you a warning to say that WDS is no longer in charge of calculating the poles and zeros, and you can change the poles and zeros yourself. So if I just look at the loop for now, that is my loop. I am crossing at 10 kilohertz, and if I double that, you will see that I am now crossing at 21 kilohertz, and I've got 64 degrees of phase margin, so it's immediately moved up to here, right? But this is now the user actually calculating these values and not WDS. So I can go back to default and put it down to automatic pole placement, and now it will do it automatically. Finally, I go to my last tab. Here is the actual component values for the compensator. So if I look at the circuit, this is my simple buck converter. WDS has automatically selected a type 3 compensator for me. And these are the values which are displayed over here. That goes into my chip, which is then fed back. Okay? Now then, these are the actual values that WDS has calculated, but these are based on these perfect poles and zeros. Unfortunately, though, you cannot buy a 3.864 kilo ohm resistor. So what WDS does, it gives you the nearest preferred values, one above and one below, based on the E96 series. So you can quickly select the nearest preferred values, and if you do that, you will see that your body plots will change ever so slightly, because these are E96 values. But the actual poles and zeros will now have a slight differences between what WDS ideally calculated, and over here you will see that even though you'd ask for 10 kilohertz of crossover frequency, in fact now you're going to get 9.8 kilohertz, mainly because you are using different values around here. Very good. So finally, it will be nice to have a simulation, and you can do a simulation on open loop, closed loop, with minimum input voltage, nominal input voltage, or maximum input voltage. And you can also do a frequency response simulation, and there's a little warning here that says that will take several hours. Now, if you're using a SPICE to do frequency response analysis, there are two different ways that you can do this. Either you can write a mathematical model, which is the way most people do it, and then it will calculate the mathematical model very quickly, and that will rely on your mathematical model being completely accurate. Or you can effectively make a SPICE behave like a Bode 100. So you can design your power supply in time domain, and just like Bode 100, inject a sine wave, wait for the sine wave to go around, have a look at the gain and phase of the sine wave that comes out. Now, as you can imagine, what you have to do is inject a sine wave at 10 hertz, wait for it to get to steady state, then measure the two sine waves. In order to get the gain and the phase automatically in the SPICE, you have to use the Fourier transforms in order to do it. It's a .4 command. So you use the gain and phase, and you plot the phase at 10 hertz. Then you have to do that 20 Hertz, 30 Hertz, 40 Hertz, all the way up to switching frequency. And every time you have to wait for it to get to steady state first. So the net result is that it will take a very long time. The good news is, though, is that that is a perfect simulation in frequency domain of your power supply without any mathematical modeling. So if you've got any errors in your mathematical model, it will show compared to what the SPICE has simulated. For now, I can do a closed loop simulation in time domain because frequency domain will take a very long time. And there you go. WDS has automatically generated your buck converter. It has automatically populated all of your component values. So if you've selected 440 microfarads for your output capacitor, that is what is appearing here. If you have selected 30 milliohms for your ESR, that is what is appearing here. The poles and zeros, of your compensator you selected, WDS has automatically populated that. If I scroll down, you will see all of these .param commands. For example, that is vref, that is cout, that is DCR, and WDS automatically written the SPICE file for you that with a click of a button you can actually simulate, and you can do that in open loop, in closed loop, you can also do it in frequency domain, and soon we're going to add a input filter design section whereby we are going to do a Fourier transform on the ripple current on the input, and based on that design the input filter. Okay, my simulation is complete, so I can have a look at anything that you like. Let's have a look at the switch current. That is my switch current. Let's have a look at the output voltage. That is my output voltage. Note that I ask for 5 volts, and if you look at the scale on this, in fact, is almost exactly 5 volts with 0.02 volts of negative ripple, in total plus or minus 0.04 volts of ripple. If I wanted to give it a unit to step, then I can do everything that I want to do in SPICE. So I've got my SPICE simulation. My design is complete. I'm happy with the performance. Finally, I go to the summary tab, and here I have got every information that I need in the summary tab, including all the values I need in order to buy my semiconductors, all the spreaders, maximum voltage, maximum current, the capacitor, output capacitor, and inductor. I've got the power loss budget, how much I am using where. I am just under 90% efficiency, just better than, slightly better than 90% efficiency. I've got the position of the poles and zeros. I've got the calculated value of the components. I've got the actual value of the poles and zeros based on the nearest preferred values, and I have got the Bode plot. Okay, so now let's do a live demo on a different power supply. Here I have got a Flyback. This is what we use in our analog power supply workshops. This is an isolated Flyback, and everybody learns to design this in the workshop, and everybody gets to measure it, because in the analog power supply workshop we've got 10 Bode 100 courtesy of Omicron Lab, and everybody will actually learn how to measure the power supply, the loop, the compensator, the plant, the ESR, the leakage and the magnetizing inductance of the transformer, and so on. So let me open up for you first the Flyback from the workshop. So that is workshop Flyback isolated. And here, let's look at the simulated plant for now. That is my plant. This is a specification that I've typed in. It's a 12 volt to 7.5 volt Flyback. this one is analog. We will do a digital shortly. With 200 kilohertz of switching frequency, 2 kilohertz of crossover frequency, and 60 degrees of phase margin. Okay? So now I have a transformer. So the WDS has calculated for me the turns ratio. It has calculated for me the primary side magnetizing inductance. It has also estimated what the leakage should be, but you must always measure. And that is what we do in the workshop, and with the Bode 100, it's very easy to measure. It has given me the world's second product. So that is what the transformer guy needs in order to wind your transformer. It has given me the primary current, the RMS current. Basically, it has given me everything that I can send to the transformer manufacturer in order to give him a little bit more information. Otherwise, the transformer guy will design for you the cheapest possible transformer that he can get away with. And when you have got these values, on the summary tab, there is a generate an email transformer design to button, and if you press that, it will list all of the specification of a transformer, and then you email it to whoever your preferred magnetics manufacturer is. The semiconductor, this is based on exactly the device that I have selected on the board. So in fact, these values are taken for this particular MOSFET over here from the data sheet. Same with a diode. I've got all the stresses on the diode. It has calculated the output filter for me. Of course, for an flyback, there is no inductor, so it's grayed out. But this is the amount of capacitance that I've got. 880 microfarads, and these are the 1, 2, 3, 4 capacitors that you've got, each at 220, giving me 880. It has designed a compensator with these poles and zeros. Yeah? And finally, these are the nearest preferred values. However, now I have an optocoupler. And of course, an optocoupler has an impact on the bandwidth of my power supply. And what I really have to do in order to design a robust power supply is to measure the bandwidth of the optocoupler, which we do in the workshop, and that gives you an extra pole. And we use that extra pole, the pole of the optocoupler, C-opto, shown here, in order to make sure that we get almost a perfect match between the measured compensator and the simulated compensator. So I input all of the data, maximum CTR, typical CTR, minimum CTR. Most importantly, I measure the position of the optocoupler's pole, so the bandwidth of the optocoupler, and I put all of that into WDS. And when I do that, it will take that into account and then design a compensator for me around an LMV431 or a TL431. Here's the one. I am using an LMV431 because that, to be honest, that's my favorite. It has got less stability issues than many of the other ones that I've had to try. And it has calculated all the component values. And of course, I have then selected the nearest preferred values, and those are the values that have been populated on this board around here. So I have got it all hooked up onto my Bode 100. My Bode 100 is still running, so all I have to do is open the Flyback isolated, non-isolated, where's the isolated? Isolated, there we go. And let's measure. Oh, it helps to turn on the power guys. Okay, power's on. Let's see what, there we go. Alright, so on my Bode, I type in my 0 to get my crossover frequency. And there we go. I'm getting 2.4 kilohertz of crossover and 63 degrees of phase margin. Okay? What I can then do is I can save this as a BodeX file and then I can go to WDS, and I can import my WDS file. So import, we've got a tab just for Omicron Lab WDS file. You open it up. Is it here? WDS voltage mode. This is not it. Labs. Flyback. WDS file. That is not one. There we go. Okay. So if you have a look, the green trace is what we simulated with WDS. The black trace is what we measured with the plant that we just measured. What I can show you, okay, now if I wanted to measure the loop, I would also measure that, and I will put it in, and I would also measure the compensator, and I put it in. Of course, that will take a long time, so I have already implemented that for you, and I've already saved it. So I can quickly show you the close correlation that we can get between the simulated stuff from WDS and the measured stuff from Bode 100. So now that you've measured it, let's open the file up again. And let's have a look. So let's have a look at my plant first. Uh-oh. I don't have the plant saved here. But that is my compensator. So you can see the compensator is an almost perfect match. Right? The gain is a perfect match. The phase, as you can see, the measurement phase loss at higher frequencies is more than the one that we calculate. And that is because of the impact of the coupler's bandwidth being more than first order at higher frequencies. We approximate it to a first order system, but in fact at higher frequencies is a higher order system, and that is why the bandwidth of the opto, the measurement, actually deteriorates away from what we have calculated. But during the region that we are interested in, it's actually a perfect match. And most importantly, the loop. I don't have the loop. We just measured the loop, if you remember. So let me quickly import from Bode 100, Flyback isolated, there you go, and that is the loop. Got an absolute perfect match on an isolated flyback with a LM341 and an optocoupler sitting in the middle. Then let's show you quickly a digital converter. So if I do a digital converter, I'll have file. Let's do a 350 kilohertz digital power supply with 15 kilohertz of crossover. Now, this is based on this board here from Microchip. We have designed a compensator for it. This is a 6-point processor, so we couldn't deal with floating point. We have to do a lot of number manipulation, and I'm going to demonstrate that for you. But first, let's have a look at what happens if I change the maximum value of my input voltage and the minimum value. Look at this line around here when I change this value. Oops, not 914. Let's say 14. And let's say 8. Oh, I expected a bigger change, but unfortunately I haven't got one. And I think I know why. It's because I fixed. There you go. You can see that if I change the maximum and minimum value of my input voltage, WDS will draw you 2 lines to show you the maximum and minimum worst case scenarios. And over here, now it actually displays the worst case crossover frequency is going to be 10 kilohertz, and the highest is going to be 15 kilohertz. Phase margin, worst case is going to be 24 degrees, highest is going to be 53 degrees. So you know at design time what are your boundaries and your limits. So let's limit that back to what it was, which is 9 volts and 9 volts, 1.5 volts amps of current, 3.3 volts. That is a real power supply over here. And here now I'm doing peak current mode and I'm doing digital control. Okay? It's 350 kilohertz switching frequency. The sampling delay is the time taken from the time you sample your output voltage with the ADC to the time the microprocessor has done all the calculations and outputted the new value of the duty. And this will cause a certain amount of phase erosion. Again, we discussed this in a lot of detail in our workshops. The crossover frequency is 15 kilohertz. The phase margin is 50 degrees. There is no transformer. Again, you've seen the rest before, so I won't dwell on them too much. The semiconductors have been selected. The important part is here. It is done, they selected the position of the poles and zeros. It has selected the height of the compensating ramp that you need in order to make sure you don't get a slope subharmonic oscillation. So he's calculated everything for you in terms of slope compensation and the poles and zeros in continuous time. But then you now got an extra tab whereby it has calculated the values of the coefficients. Now, if you've got a floating point processor, and there are some about, I mean, TI does some, you can copy to clipboard, and you can just paste. There you go. These are the coefficients of your compensator done within minutes of you designing your power supply. If you don't have a floating point because it's expensive and you're going for a fixed point processor, we've got a microchip tab, and here you can do lots of number manipulation. This is fixed point. It's, again, WDS will automatically align all the numbers for you. Again, you've got copy hexadecimal to clipboard, and you go paste. These are your coefficients. These are the bit shiftings that you need to do. That's your reference. This is all nice and easy for microchip. And for TI, we've got another tab which does exactly the same thing in TI's IQ math format. You paste. There we go. Again, designing a digital power supply could not be easier than this, mainly because we have done all the background work for you, and the software will automatically calculate intelligent coefficients, so it takes the guesswork out of it. And we discuss how all of this is done in our workshops. So I think I've come to the end of my presentation. We have done the live demo. Let's see, shift 5. I've demoed all of these live for you already, so I will not go through them. This shows the perfect match that we get with the optocoupler. That is the circuit of the flyback that we use in the workshop. This is the match that we get when we do a proper measurement. Again, you saw that live earlier on. That is the compensator. That's the loop. And that was the plant. So our forthcoming workshop, the analog power supply design workshop, is this one is sold out. So I'm afraid the December show is completely sold out at the moment. March show is in Garching, Germany. That has got seats available. Then we've got a digital power workshop with microchip. That is in February in Karlsruhe in Germany. Then we've got a digital PFC workshop with TI. That is also in February, and that one is in Garching, Germany. And then we've got a digital power workshop, and that is with TI C2000, and that is in April in Garching, Germany. I think my 45 minutes is up, so thank you very much for listening, and I am open to questions, and may I please ask the moderator to come in, and I yield the floor to the moderator. Thank you.
Ali, thank you very much. I'm always impressed how much you can talk about Power supplies.
Says the same thing. My wife says, I'm always impressed how much you can talk.
About power supplies. So we will be still here for some minutes for questions, in case someone has some questions. Please post them to the chat function. You can either directly post them to Ali or to Omicron customer support, and we will be happy to answer your questions, in case there are some.
Guys, can I just add something? The WDS is available for sale from our website, but if you attend the analog power supply workshop in March, in particular this one, you will actually get a full license free of charge thrown in with the price of the workshop.
Okay, so until now we did not receive a question. Maybe you did explain everything already?
Or maybe nobody listened. No.
No, I think that some people listened, Sally. Okay, in this case, I thank you very much for visiting our webinar. We will have a next webinar series in approximately 1 year, and of course we will send you the invitation letters again, and maybe we can have Ali as a first speaker, as a guest speaker. Let's see what topic we can find. And I wish you a nice day or a nice evening in whatever time zone you are, and see you again in our next webinars or somewhere else. Goodbye.
Thank you very much. Bye.